Intracluster light is a separate component from the brightest cluster light, and it has significantly lower stellar ages and lower metallicities than anywhere else in the brightest cluster galaxy. I'm coming from California Polytechnic State University. It's about an hour and a half up the road in San Luis Obispo. My name is Louise Edwards, and my collaborators on here especially want to highlight the undergraduate collaborators from CalPoly and also from Yale when I started this work at Yale, who helped with this work. So 1, 2, 3, 4 of them are now PhD students in astronomy, and one is a high school teacher in physics. So I'm feeling very extra proud of that. So brightest cluster galaxies and the intracluster light and IFU view. Our question is how we go from large, red and dead, old systems that we see so commonly in the high-density cluster universe of today, from, presumably dusty, young star-forming galaxies at some point earlier on. So what can today's brightest cluster galaxies tell us about early star formation? And what is the origin of the ICL, of the intercluster light? How much do cluster processes contribute? How much can we think of the buildup as the ICL, kind of like we've been thinking a lot about stellar streams around the Milky Way, where interactions with the main body, the brightest cluster galaxy in this case, matter compared to interactions with other cluster galaxies, and the ICL having a component sort of apart from the brightest cluster galaxy directly. So the intercluster light is fairly difficult to study historically. Of course, now we have HSC and soon we'll have LSST, but historically it's quite difficult to find. Here's a beautiful galaxy cluster, and if you stare for very hours, if you stare for like 20 hours, then you get this beautiful image, and Kluge and co have done this for about 100 local galaxy clusters. And the intercluster light is, of course, this diffuse light that you see spread amongst the main galaxies of the cluster, centered on the brightest cluster galaxy. The intracluster light actually has a very high fraction of the light of the entire cluster. That number varies a lot depending on studies. But also a current question right now is how that, or if that fraction of cluster light has changed a lot over time. So you'll see studies where the fraction of the intercluster light, so the total light of the cluster, varies greatly, changes quite a bit from the higher redshift universe to today, and also where it doesn't change. And how the intercluster light grows, how that fraction of intercluster light grows, can tell us something about the formation of the ICL, and possibly the brightest cluster galaxy in general. So positive correlations between the brightest cluster galaxy and intracluster light, brightness, and the cluster mass and radius and richness imply that the brightest cluster galaxy and the intercluster light growth could be coupled. So can the properties of the ICL discriminate between origin scenarios, as I was suggesting earlier? So let me take a moment to run through the popular origin scenarios that people talk about. So this is how does the intercluster light build? So violent relaxation after major mergers, in particular with the brightest cluster galaxy. That is one common route. Pre-processing in groups. So, you have mergers or pass-bys or whatever in groups stirring up a lot of intercluster light, and the groups bring that light into the main cluster. In situ star formation is sometimes tossed around, although generally not considered so much these days. The disruption of dwarf galaxies as they plow into the cluster is a possibility. And the stripping of massive satellite galaxies, so like L-star type galaxies, is another common route that a lot of folks are finding to be important. So we've seen color breaks in the colors of the luminosity of the light, and this suggests that the light is a different component than the BCG. So breaks in the luminosity, but also breaks in the kinematics of the ICL. It implies that it's a different component than the brightest cluster galaxy, even though when you look at it, it looks just like it could be an extended amount. But this is showing the colors of the ICL, so the blue line, around the core of the Abell 85 cluster. And it's showing very, very blue colors compared to all of the galaxies in the cluster. So it seems to photometrically be bluer, have a younger component than the main galaxies. That's observationally. Theoretically, folks have done a lot of work in making ICL in their simulations. So, but they don't always show the same thing. So for example, in Murante, 2007, about 75% of intercluster stars come from the progenitors of large red galaxies in the cluster, compared to other studies such as Martel 2012 and Contini 2018 that find that also Milky Way, like L-star galaxies, are a more important component for the BCG, for the ICL. So these photometric studies are quite common, and these days have been done on HST data and even JWST. But it's more difficult to get a spectrum of the ICL. It's very faint. So that's where our project came in. We observed 23 brightest cluster galaxies using the WIN instrument called SPARS-TAC that has these very fat fibers, lots of them. And we observe 3 pointings using this instrument. And what we do is we separate the light from the core of the brightest cluster galaxy, the outskirts of the brightest cluster galaxy, and then the real outer regions, which we're calling the intracluster light. Okay. Of course, you don't see anything in these fibers in the intercluster light. It's so faint, but when you add up what's essentially 80-hour spectrum by combining all of the ICL spectra, we do get a spectrum that pops out. So we have these 24 spectra of intracluster light for these local galaxy clusters. So these are things like Abell 1795 and Abell 85, you know, these massive nearby Abell clusters. What we do is we use full spectrum fitting to get an estimate of the ages and metallicities of these systems. So we model the spectra using starlight, and our best fit spectrum gives us an output of a fraction of stellar populations that made it into the final spectrum that was the best fit. So here's an example. Nice brightest cluster galaxy from Sloan. Our footprint, okay, this is Abell 193. And then just to be honest about it, right, this is the Cluj data, right? So to be honest about it, we're getting brightest cluster galaxy plus intracluster light, but we believe we're far enough into the intracluster light that the spectrum we get is certainly polluted by the BCG, but is beginning to be dominated by the intracluster light. Okay, so our project then is, if we look at the brightest cluster galaxy, the intracluster light, do we find breaks in the stellar populations and in the kinematics where we are going from brightest cluster galaxy to intracluster light? So look at the stellar populations and see if we have a break. Indeed we do. On the left is age, and on the right is metallicity, and the x-axis is how far you are from the core of the cluster, with 1 RE being right here. And if you concentrate on the ages, you notice that the ages, especially in the high mass bin of clusters, which is on top, are very, very flat until you get to 1 RE, where they start to plummet. On the other hand, the metallicities, they also fall, but they fall in a much more smooth fashion. This is consistent with photometric studies. So for example, the study on the frontier fields by Montes and Trulio a few years ago, where they also find ages based on colors that drop about 40 or 50 kiloparsecs from the core of the brightest cluster galaxy. We can take the population synthesis, and instead of showing average numbers for the age of metallicity, we can look at the fraction of the different populations that went into the best fit. So when we do that, looking at the core of the BCG, we see very old, very metal-rich, so purple, stellar populations dominating, and very few young populations, right? But when we look at the intracluster light, certainly many of the populations overlap. It's to be expected. But we see, up to about 50% of young stellar populations. Again, to be honest, when I say young stellar populations, I'm talking about less than 8 gigayears. And also you want to take all these numbers with a huge grain of salt because they're based on this one fitting code that we used. We did a lot of tests changing various parameters. Although the numbers, specific numbers change, we always find that same drop in ages at about 1 RE and smooth decline in metallicities as well. So metal poor stars are much more common in the intercluster light than they are in the brightest cluster galaxy. And these stars presumably formed in shallower potential wells because we see this decline in metallicity. So this supports both the major merger formation scenario and tidal disruption, so L-star galaxies, scenarios for the origin of the ICL. So this is our idea. I like to show this image created by Theo for us that summarizes some of our work, because I had an amazing opportunity to work with a graphic design undergraduate, and she made anything pretty that I ever show, they made. So it's been amazing. And just as a side note, they got so excited about astronomy after their undergraduate degree, they are now currently in community college doing physics courses to come back and go on in the physics world, potentially. Anyways, conclusions. A proposed formation scenario for the ICL. The brightest cluster galaxy and the intercluster light tend to have different properties. So the brightest cluster galaxies are older, they're more metal rich. I didn't show this, but they also have low velocity dispersion compared to their own intracluster light. These differences are parameterized by a slope. We can, how much does the age change? And the slope is determined by host cluster properties, not BCG properties. In many cases, the intercluster light velocity dispersion matches the dispersion of the host cluster. This suggests that the brightest cluster galaxy and the intercluster light have a different origin. The brightest cluster galaxy formed first. 87% of the stars have ages over 10 billion years, corresponding to formation redshifts of about 3 or greater. The intracluster light is therefore formed afterwards, and a wide range of ages in the intercluster light that we see suggests a slow formation process taking place over a long period of time. So these data are inconsistent with the ICL having a large red galaxy origin, so only being formed from mergers with the brightest cluster galaxy and other large red galaxies. There's a component that we have seen of stars that formed at about redshift 1. So there's a popular scenario for the origin of BCGs put forward by Toft in 2014, where you start very early times with a gas-rich merger, go through a dusty nuclear starburst phase, some quenching phase, a compact quiescent galaxy phase, and then a dry merging phase, which adds mass to the brightest cluster galaxy and also puffs it up. And we're proposing that about redshift 1, maybe the creation of the ICL is also happening from minor mergers. We speculate that the intercluster light could originate then from intermediate mass galaxies destroyed by the tidal field of the BCG itself. So L-star galaxies are important, but they're being destroyed by the field, the tidal field of the BCG. This would explain why the BCG is always older than the ICL. And this is a nice place to wrap up the story. All right, we have agreed with everybody who did photometric studies. We agree with many of the observations that look like this slow period of formation with interactions with lower mass galaxies is important. Very nice little bow. So in 2023, so in the last 3 months, there have been some very interesting papers on this. One is by Zhu and Ji, who look at Hubble Space Telescope data of brightest cluster galaxies, intercluster light, at a redshift of 1 to 2. So already seeing intracluster light at redshifts of 1 to 2. So if we put their work in context with much of the work that has been built up in this field over the last 10 or 15 years, and we look at the intracluster light fraction, which we saw an earlier diagram of this at the beginning of the talk, as of, over cosmic time, now not just going to redshift 0.6, but going all the way to redshift 2 with this new study, it looks like the intercluster light fraction is not changing, which is different than what I just said. Also, very recently, Coogan from the Sears data from JWST have imaged this brightest cluster galaxy in formation at a redshift of 1.85 and already been able to identify some intracluster light in that image, okay? So they're showing you this wide field here because there's all that intracluster light already at a redshift of 1.86 that they see, but nothing, in the outskirts. So it seems to be real light. Yes. So, okay. I've been very excited to be here for the last several weeks, both not just for this conference, and thank you so much, but also for the Cosmic Web conference that happened earlier. As I'm starting to think about my own research and how we go from detailed, targeted observations to making the most of these huge data sets that are coming online. In particular, LSST is what I'm interested in. And I'm interested in using LSST to look at intracluster light. It's going to show us quite a bit. On the short time set, that's probably the 10-year data. So on the short time scale, I'm interested into testing how we can get it out. And anybody who is interested in LSST or intracluster light, we have a day and a half left. Please come and talk to me. Thank you.
Talk. Do we have any question?
Yeah, really nice, thanks. I was interested just in kind of the point you made at the end there about intermediate mass galaxies kind of being stripped by the BCG. And I'm just trying to think about that as a kind of scenario. It seems to me, so you see this, this ICL really far out from the BCG, right?
Yeah.
And wouldn't that,
oh, yeah.
if you look at this in a model basically, and put an intermediate kind of mass galaxy, have it be tidally stripped by the BCG, you would then be able to say whether we see this or not out to these extent and this radii. And I was just wondering if either you or somebody else has done that kind of study.
Yeah, I haven't. That's I can't. That's a good idea, and it brings up the point of the caveat the limitations of our study, okay? So we're looking, you know, if I were to put my fibers on there, on this 50 kiloparsecs, I would probably catch, you know, these two big guys beside, but not that extended stuff out there. So, I mean, you could imagine that it's not one simple, it probably isn't, one path that creates the ICL, but rather multiple channels. And I could maybe imagine that ICL created further away from the cluster potential might have a different origin than the ICL nearby. It's a good question and something people should pursue. It's a lot harder to get this spectroscopic data out there.
Right. Yeah, I think it seems like prime for models.
Yeah.
And maybe they already are.
Hi, Megan Tillman here. So I have never heard of the ICL before, literally 20 minutes ago. And I was just curious if something like this could be used to calculate like escape fractions from galaxies, or if it's just so thought of to be so far removed from galaxies itself. Like, I don't know if the
escape fractions from galaxies.
Like-
we could maybe talk more about that later. I'm not
Okay,
sure.
yeah.
I've never thought about that before. What people usually use this for is to think about, is it like is it sort of, can I use it as like archaeology on how the core of the cluster built up, right? If you got really stoked on ICL and are now about to head deep into the literature, some of the early images show these really exciting, like almost like fronts and tails. And something to keep in mind is that the data reduction for the imaging is really, really difficult. And it's really important to do, in particular, like really careful flat fielding. So it's important so if you delve into some of the earlier work, it's definitely important to keep in mind that there's some popular images out there that show a lot of structure that's actually not real structure. But that aside, we still think that examining the ICL is a great way to figure out how the cluster itself built up. Yeah. Sort of parallel a little bit with the streams.
What do you think is the most interesting unresolved theoretical question about the ICL?
I mean, okay. I think that, okay, we've seen a lot about how the low mass end, dwarfs, is really amazing at constraining models, and in particular dark matter. And so brightest cluster galaxies probably don't have that power, but they are found in an interesting place, right? Brightest cluster galaxies are almost always at the bottom of the potential well of the cluster, and lots of additional physical processes can happen to them compared to other galaxies, like especially if they're in a cool core or something like this. My point is, I think that this system is an interesting system to get right in models, and hopefully has some constraining power there, right? So when did this ICL actually build up, right? When were these brightest cluster galaxies initially forming? I think, the amount of ICL, I can't see how it doesn't have anything to do with some of the major mergers with the BCG. So I think that, theoretically, I think the most important questions theoretically about the ICL are exactly when did it build up? And did it build up the way we think it did, how we put it in the models right now?
Okay. Hi, John Wu. Yeah, thanks for this great talk. So I'm curious, when you saw evidence for younger stellar populations in the ICL, even though you mentioned that in situ star formation may not be a popular mechanism for building up the entire ICL, do you think there's evidence, and also with recent JWST results, do you think there's evidence to say that a sizable fraction of the ICL is formed younger from things like ram pressure or tidally stripped pockets of gas that can collapse?
That's a great question. So young for me can be as young as 7.9 gigayears, okay? Because the brightest cluster galaxy, the core of the brightest cluster galaxy has like, you know, the oldest ages that your star fitting, you know, population fitting code can have. That's what the core of the BCG has as its ages. These were probably, you know, dense peaks early on that the core of the BCG, those stars formed a long time ago. So when I talk about young ICL, it just means significantly younger than the core of the BCG. And I forget what your question actually was.
Well, I mean, yeah, like I think there was some also a little evidence that, you know, with JWST observations that there are recent bouts of star formation, maybe not, it's outside of the galaxies, outside of host galaxies, which maybe
Yeah.
But maybe that, I don't know if that's consistent with what you're seeing.
Okay, I think I know what you're talking about now. The ages work out actually for this 15% here. You know, I mean, modulo the cell population fitting is difficult, but yeah, the ages here for this young part of the ICL work to fit with that those new little stars from stripped galaxies that were formed. And so that would be very, very exciting as well. That's also opposite to the other JWST observations, what they show. But again, I think plays into this light is it's probably being jiggled up from large galaxies as they're being violently relaxed. There's they're at the core of this cluster, there's all these other processes going on. I think the question is just, a great question is how far away from the core of the cluster can your process be and still have those stars that are removed end up at the core of the cluster? And I don't know that answer, and that's been something I've been thinking about since I've been here. But those numbers do work out.
Sucheta Kure, thanks for a really nice talk. I learned a lot about ICL. I was wondering if you have looked at sort of the directional dependence of the composition of ICL, meaning with respect to the inclination of the galaxy or something like this, or when you look at the cluster itself.
People have looked at that, and they see there's some alignment. There's a lot of alignment between the BCG and the ICL. And people have also looked at the alignment of the BCG and the cluster itself. And people have looked at the alignment of the BCG and the main filaments that come into the cluster. And I think with, well, you know, that Cluj study actually has 100 systems, so there might even be enough now. But with Rubin, there will be so much ICL data. And I was talking to Peter, and he has a large sample of ICL as well. But you could absolutely, definitely do that. And I'm sure people will, something I would like to do with the Rubin is look at the alignments from the scale of the BCG through the ICL, the cluster, and the main filaments that feed the cluster. I think that would be super interesting. With the spectra, that's really tough. Like, we had to add up 80 fibers, you know, each taken with an hour to get our, you know, our spectrum. So with spectra, that'd be really tough.
Thanks.
Again,